Hello, this is video 31, and I feel good, I feel strong, I think I can do this. Let's use the exact same keys that gave us that all stringy, strung out binary search tree and see if we can build a 2, 3, 4 tree with that. 2, 3, 4 tree. Example. Wild and crazy nodes, you remember, 3 data values in the node, 4 pointers to children. I don't know how we're going to do that. Well, we're going to do it like this. I'm not going to show the root or anything. We're going to start, of course, with one internal node. And that internal node, until further notice, has nobody in it but A. And rather than get black all over my hands, I think I'll do the pointers. But no, I'll have to do it here. 3 data values. What I will do is this. The data values could change. So I'm going to put A up here way at the top in case I have to mark it out and put a new value beneath. You'll see that happen later on. A, done and done. B, well, of course, we start at the root node. Where does B go? Well, A is less than B. In other words, B is greater than A. So the first check that we would do is there a child down here for things that are greater than A? There is not. So B will just go in the next data space. I'm shooting flies with elephant guns right now. I think I'll just push this forward until we actually need to look down there. What about Z? Z is greater than A, Z is greater than B, and there's no third data value, so I would look, I'm going to have to say it, I would look here at this third pointer, see if there's anything down there for Z to go be compared with, but there's not, so Z just sits right there and everybody's happy. Oh, if only we could stop right there. And our 2, 3, 4 tree, that's a valid 2, 3, 4 tree. There's only one node, it's the root. It's got 3 data values in it, of all things. But keep it up with where I am. When we insert Y before we even compare Y to A, we look at the node. This is the way down the tree, even though there's no place to go down from the top. It looks at this node and realizes, you know what, that's maxed out. Before I go any further, got to do the split. When I do a split, what happens? Well, A moves into its own place. Gets a node of its own, and it would take any kids, but they're not any kids. Z gets a node all to itself, like so, and B would move up to live with its parent, but there is no parent. So what happens is we have to make a new internal node for the root. All of a sudden, 'tis vastly different from the BST. Once the root, always the root. Once the king, always the king in a BST. The root might very well get demoted down to being one of these, would probably keep this data structure rather than reallocating everything. So this one would keep the A, and the B and Z are moving out. The B becomes the new root of the whole tree, and look what we got here. At this point, if I go no further, this still fulfills the requirements to be a binary search tree. Let's do an in-order traversal. A, B, Z. Done. Okay, now what? Well, we inserted Z. Let's insert Y. Look at this. Now, here I'm going to try to remember to put all the steps in there. This is a fairly involved put function. I look at this and see if it's full, to see if I need to pop it open and split it before I go any further. It isn't. So now I start the comparisons. Y is greater than B, but there's no second data item, so I look and see if there is an internal child of B to the right, and there, in fact, there is. I look and see if this is full. It's not full. So I compare Y to Z. It's less. I would look and see if anybody's down here. There is no one down here, but I don't put a new node with Y down here. I make Z scoot over. See, I told you this was weird. Y is less than Z, so Z got to move over and now be the second data item, and Y is the first data item. You see what happened there? You might want to rewind 30 seconds and watch that happen again. Let's try this. Let's insert C. Look and see if this is full. It's not full. So we start the comparisons. How does C compare to B? It's greater. We look and see if there's a second data item. There is not. So we look and see if B has a second child that's internal, and it does. We take a peek and see if this is full. If it is, we better pop it. No, No, it's not full. So we come down this, pardon me, come down this direction. And now I wish I had made these nodes even taller. I am going to make this one even taller. One moment, please. Oh, that's ugly. Now then. Okay, C, we start doing the comparisons here. If C is less than Y, we don't even need to compare it to Z. We found the place where it goes. We're not, hang on 6. I got ahead of the game again. C is less than Y, I would look and see if there is an internal child down here. If there is a node down here to the left of Y. Since C is less than Y, I would move this direction to see if C needs to go down here somewhere. There is no down here somewhere. There's nothing down here. So Y and Z both have to move over. Move over Z, move over Y. Now it's made room for C. And I checked it off too quickly. And the smoke clears, and we have still a valid 2, 3, 4 tree. How would we do the in-order traversal? It's really weird. It would go A, B, C, Y, Z. And they're still in alphabetical order. Uh-oh. Something's up. Here it goes. What about X? X is greater than B. Well, first of all, B's not full. This node doesn't pop. X is greater than B. I look and see if there's an internal child. There is. I look to see if that node is full. It is. So this has to do the split again. And of course, there's not room up there. So I'm going to have to do the wraparound. Down here, when that splits, this is the root of the whole tree. And there's still a B up there. I'm going to leave B unwritten at the moment. And A is over here, minding its own business, not causing anybody any problems. And that's still going to be the left child. But look, this is the node that splits. When this splits, this actually becomes 2 children. Not just the second pointer anymore. The second pointer is going to point to the node that will just have C in it. I'll draw as I talk. The third pointer, this one, is going to point to a node, a brand new node that we dynamically allocate that just has Z in it all by itself. Third. Now then, when Y comes up, oh no, where do we put it? Well, Y is going to go after B. Y needs to be between these 2 new kids here. Y needs to be between C and Z. So Y would go right here. Oops. I made those tall for a reason. Y goes up here, and now I can put B. The reason I didn't write B, there was the possibility that the kid that comes up is the new first kid. There's a lot of things that could happen here. But in this case, since it came up along this pointer and this one split into these 2 pointers, then it's almost like this little dividing line points at where the new data value will go in the parent. The old data value that moved back in with the parent. Maybe that's a different way to say it. This is still a valid in-ordered tree. A, B, C, Y, Z. It's just kind of weird. A zigzag kind of traversal thing going on here. Okay, moving right along. What about X? This is not full. We don't have to split it. X is what? Greater than B, W, X, Y, Z. X is less than Y. So we would stop right there and check and see if there is an internal node. And there is, look at that. Between B and Y, because X falls between those 2, I have to check and see if there's an internal child here. In fact, there is. X is between B and Y. So I follow this and look at this one. First, I check and see if it needs to split. If it needs to split, then I'm going to have to do some shuffling in the root node before I go any further down the tree. But it's not full, thank goodness. So all I do is compare. X is greater than C, where I am. So I look to see if there's anything here. There is not. So X becomes the second data value in that node. Again, I checked it off too soon. I'll wait and check off W after we do it. Here comes W. And I'll have to sing to get this in the right order. This is not full. We don't split the root. It's certainly greater than B. WXY. It's less than Y, so we got to follow the same pointer again. So W is going to come this direction. It's greater than C, WX. It's between these two. So if there were an internal child here, we would have to follow this pointer, seeing if it's full and pop it or if necessary. But there are no internal kids, so WX. Yes, W is less than X. X has to move over, and this gets copied over with W. Now I can check it off. And everybody's happy. Until V comes along. V is going to mess things up. Let me see here. V is greater than B, UVWXY. Of course it's less than Y. I follow this pointer, but look, when I take a peek ahead at my second child here, I see that that child is full. So this is going to require another restructuring. This is going to require a split. Well, let's see. I'm going to have to make these smaller or they won't fit. I'm going to squash the A node over here. A is still minding its own business. You know what? I don't think anybody's going to come this direction. The only thing less than B in the alphabet is A. So you are safe. A, you are safe. But we don't know that officially while we're just trying to follow the algorithm here. A is over there by itself. Here's the parent in the sky, which in this case is the root of the whole tree. Who splits? Here's a weird one. This one splits, but it has siblings to the left and to the right. So what's going to happen is the Z node pointer is going to have to move over and become the last pointer, the last child. A is the first child, Z is the last child. It seems poetically just somehow, doesn't it? From A to Z. Z has to move over to make room for the pointer to the new node that's going to be created when this gets split. When this gets split, think about it, we'll have a node with C all by itself and a node with X all by itself. These are really skinny nodes. They're not drawn to scale. They're actually all the same size. So there's C all by itself in this one and X all by itself in that one. So far so good. And those are the middle children. B is still in. Now look what happened here. When these push over and I'm sending up a data value, the data value goes between the two kids that resulted from the split. So this rising data value here, W, that's going to be the middle child. So Y has to scoot over. See what happened there? Going from here to here, this node, the one that's between the two internal kids, that's the one that's split. So the child pointer has to move over. The data value has to move over to make room for the rising W that resulted from the split. So here we are. We've got a pointer to A, then B, then C, W, X, Y, Z. And it's still in alphabetical order. They look like they're in jail down there, don't they? Oh my goodness. What was all that about? That was all just in the name of trying to insert V. So this was a preemptive split. Now, this is going to refer back to one of the weird notes I told you about. Here's a weird note. Part of the split, the reason for the split is, so when we get to the bottom of the tree, there will always be room for the new data value that we're inserting. Since V was going to try to go this direction, we got to make room for data value V somehow. So that's why this node had to split into two. Now we start with the parent where we preemptively caused a split and we do our comparisons again. V is greater than B, U and V, W is less than W, so it does go this direction, comes down towards C. We compare it to C, it's greater, there is no second data value, so V becomes the second data value. V is before W, right? U, V, W, X, Y, Z, yes. Okay. Now then, I don't want to start another video. I'm going to keep going while I still got some momentum here and just get rid of everything. This is the current state of the art right here. That's our current tree up through V. And there are only two data values to insert. Only two keys. That's not the entire data value, of course. That's the key that will find the data value for us when we actually start doing lookups. So, the entire tree. Let's admire it while we can. Why? Because look what happens when we insert U. we don't even start comparing data values. The very first thing we'll check is, are you full? If you're full, you get a split. So this one is going to split going back this direction. There's no significance to the direction of the split. That's just where I have to draw the pictures. When this one splits, this is the root. When this one splits, there becomes a brand new root of the entire tree. In fact, what will be alone at the root? The middle value, the W will be up there. And it splits into two. This is the most significant split so far. Watch this carefully. The root itself splits into two nodes. One of them has the first data value alone in it as its first data item. The other one has the last data value in it alone as its first data value. Let's pause and reflect and see what happened there. What happened was this had to split because it was completely full. We're trying to put U. We're going to put U in this tree. And it split because the root was full. Whenever we encounter it, we don't even look to see what the data values are. We don't care. We got to split to make sure there's room. Now, one more thing. If there had been no U and D to mess things up for us, this is a perfectly fine 2, 3, 4 tree. We don't have to split it just because it's full. We split it on the way down the tree, which is code words for before a recursive call. We split on the way down the tree to make sure we have space for a new data value to go at the bottom. We've got space for kids that need to move back in, all that stuff. So we preemptively make space before we even think about inserting U in the tree. That splits. Okay, I've said that over and over. And who gets which kids down here? There are 4 kids. B gets the first 2. A, and CV. And Y gets the other 2, X and Z. I know your picture would look so much better than this. I can't wait to see your notes. Look how big the tree got, just going from here to here, and we didn't even insert any new data yet. This was just a split to get ready. When we did that, if we do the try to do the traversal thing, it will go A, B, C, V. As soon as we hit a node here with no kids, we just do all the data values. A, B, C, V, W, X, Y, Z. So it's still in order. Now we look at U. A, B, C, D, U, V, W. U is less than W, so come this direction. U is greater than B. We look and see if there is something to follow here. Yes, there is. Is it full? No, it's not full. So what? U is greater than C, U, V. It's less than V. Move over V and U. Like so. C, U, V. U, V, W. Yeah, that's the right order. Well, after we accomplished the split, that was fairly painless. Oh, we were living in La La Land. Look and see. You can tell what's going to happen here. I'm even going to have to get rid of this thing. These things get monstrous in a hurry, do they not? I'm going to have to draw smaller or it's not going to fit. When am I going to learn my lesson? Draw smaller. Here's the deal. We're going to insert D. D is less than W. You can see where we're going. D is greater than B. Come this direction. Bonk. When we hit one of these things on top of the head and it's full, it's got to split. So I can do all of this part of the tree without looking. And I'll even squash it over here to make space for the new arrivals. W, its second pointer points to Y. I'll even make it smaller because they're bit players in this operation. And then X and Z are Y's 2 kids. There. How could I do that without even looking at anything? Well, D is going to go this direction. It's going to go left, so it's not going to leave that. I mean, it's not going to disturb that at all. It is disturbing over here. We got as far as B, but when we came this direction, this one's going to have to split, which means U is going to move in with B. So instead of B being all alone, it'll now have a partner in here. B and U will be together. B's left child will still point to A over here. And what? Instead of having just one pointer to a second child, we'll now have 2 pointers to a second and third child. I don't know what that is. That's supposed to be an array of 4 pointers across the bottom. For all the talking about drawing pictures, my pictures are really pretty sloppy, aren't they? I have to admit that. Okay, C is the second child, pardon me. U moved in with the folks, and V gets a node of its own. And B and U now is the left child of W. And what? V got a node of its own. What was all that about? Well, we're trying to insert D, bless its heart. And D was greater than B. When we came this direction, we saw that this node was full. So we had to pop it open and split it into 2 nodes, one for C and one for V, and let U rise up and join the parent node. Now then, when we were right here and took a peek and saw a split, that means we didn't go any further down the tree. So we're still right here. We call the split operation on one of our kids, but we don't leave where we are since we're taking a local view in our recursive algorithm for put. So we look and see, now we can start comparing for real. Did things change? D is greater than B, but it's less than U. No, so we still got to follow this second pointer. D is greater than C. Oh, darn, there are no more kids to look at down here. So it stops right here and inserts D right there. Done and done. Now then, what can we observe? Well, it doesn't look like it over here because I was so cramped drawing the picture that it was all crooked and everything. But the nodes at the frontier, in other words, all of these boxy nodes down here that look like jails, those are all at the same level in the tree. If I start right here, it takes me 2 arcs to get back to the root. If I start right here, it takes me 2 arcs to get back to the root. This is completely balanced. It's flat across the bottom even though it looks bumpy. It looks split level, but it's a single floor. What else? Every insertion that we did, because of the splits on the way down, every new data value that we put in a node went into an existing node. By the time D got here, this node already existed. We didn't make a new node for D. We peeked ahead and annexed some space down here just in case. And the weird thing is, if I were to insert D again and this were full, then it would have to pop it again on the way down, just in case it needed space for D. At this, the way it is now, it's going to get down here and find out D's already there, so it'll return false. Isn't that a weird thing? That should have been an additional cryptic note. The structure of the tree may change even on an unsuccessful insert operation. Why? Because we've got to prepare for, we got to get ready for the worst case. If I were, let's go back in time. If I were inserting C into this tree, then what would happen is once I got this far, I would realize, well, I need to go this direction, but this node is full. So this node would still get split and all the restructuring would occur only for us to get down here and find out, you know what? There's already a C in the tree, return false. Don't do anything else. So new data values go at the bottom of the tree. The tree gets restructured on the way down, which means any restructuring we need to do is done before a recursive call to put. What about the kids? I don't know. What could we say about the kids? They are in kind of a weirdo, bizarro, Frankenstein, BST order, but they are still in alphabetical order. The traversal, as you can tell, is going to be a little more involved, but it still works. It still prints things out in order. What were my 2 cryptic notes? I already put those notes away. Cryptic note number 1, new data always goes to an existing node, no children, got that. During an insert operation, we got to split it, got that. Okay, here's some more notes in a horribly disfigured set of pictures. Yikes. Observation number one, I've already observed this, I'll make it official. Number one, all nodes with no children are the same distance from the root. In other words, all of the nodes at the bottom of the tree are level. It's a balanced tree. They're at the same level from the root. Oh, I didn't make this observation, but you did. Back in time, it's already been erased. How does the tree get any taller? We don't add nodes at the bottom. It gets taller when the root of the whole tree has to split. Then all of a sudden our tree is one level taller than it was before. These kinds of trees, we're in bizarro land anyway, these kind of trees grow at the top, not the bottom. It gets taller when we have to split the root node. Here's another observation that's unfortunate, I suppose. Even though it's balanced, yeah, that was our goal, it's balanced. If most of these nodes are full, then we still don't have that delicious little order log base to have been searched the way we like. Why is that? Well, visualize this, if you will. What if this node has more than one data value, this node has more than one data value, and you keep going to the right? Then keep going to the right. If we take the rightmost child each time, that means we had a miniature order in search inside the node. Think about that again. Order in means you have to look at it sequentially. You can't take a shortcut. We've got many order in searches, many M-I-N-I, not M-A-N-Y. We've got miniature order in searches possibly taking place within nodes. So even though this is great, it's, well, great, easy for me to say. It's messier than a binary search tree, but it does work. It's balanced. And it's order log n with a multiplier and a constant. So it's still order log n, but we do have this little problem of creeping miniature order in searches within the nodes. Food for thought. Maybe we can fix that, maybe we can't. At any rate, ladies and gentlemen, here is our 2, 3, 4 tree, and I'll see you online.